Part 4. The ether is dead. Long live the ether. During this time between 1799 and 1887, scientists in different fields of physics were hard at work on electricity and magnetism. The invention of the Voltaic pile in 1799, the first electric battery, allowed for the first time ever a steady continuous stream of electrical charge, which was thought to be a kind of fluid that flowed through the wire like water flows inside of a hollow tube. Before this continuous flow of electric fluid, it was demonstrated that static electricity can be used to reduce chemicals like tin, zinc, and antimony from their salts, which was something that was already known by alchemists, that fire will cause the transformation of matter in a process called calcination. The first productive use of this continuous flow of electrical fluid was used in chemistry experiments to reduce chemical compounds into their elements, as it was discovered by William Nicholson and Anthony Carlisle in May 1800 when their Voltaic pile's two wires were placed in water. The water completed the circuit of the battery, and the two ends of the wire produced bubbles, which turned out to be the gases of oxygen and hydrogen. This discovery led scientists like Sir Humphrey Davy to use the Voltaic pile to conduct chemical experiments, such as isolating, for the first time, chemical elements of calcium, strontium, barium, magnesium, and boron, as well as using the piles to create an arc lamp, the first incandescent light, which, despite our taking for granted view of light bulbs, was a huge deal, as this showed that there was some connection between electricity and light. That electrical sparks produced light sufficient enough to light a room. April 21st, 1820, Hans Christian Ørsted found that a magnetic compass needle was moved in the presence of the electric current, which was supplied by the Voltaic pile. Ørsted had no clue what was occurring, simply that it was doing so in spiral circles around the wire, and also that they were in planes perpendicular to the wire. The effect strength depended both on how close to the wire it got and the magnitude of the current. That reversing the current reversed the compass needles, and that it penetrated all non-magnetic bodies, whereas it moved all magnetic bodies due to their resistance of the electrical conflict. This was the first connection between the two natural phenomena, and its publication caused an explosion of scientific discoveries. In fact, it is likely one of the most important discoveries in human history. Within weeks, André-Marie Ampère had already developed Ørsted's discovery into a mathematical formulation on electrical and magnetic interaction, and later formed Ampère's force law, which describes the production of mechanical force by the interaction between the electrical current and the magnetic effect related to it. This inspired Humphrey Davy and William Wollaston to attempt to use the electric current and the magnetic effect to create a mechanical action, otherwise called an electrical motor. But the pair failed due to the fact that they thought the circular magnetic effects were spiraling along the wire. Davy's student, Michael Faraday, in 1821, picking up the pieces of his supervisors, discovered that the circular effect was not spiraling up the wire, but rather that it was more like a set of enclosed cylinders around the wire, which allowed him to create the first electrical motor. In fact, he created two. In 1825, British electrical engineer William Sturgeon invents the electromagnet, a horseshoe-shaped bar of iron with a loosely wrapped coil of copper around it. When a current was run through the copper coil, the magnetic effect of the currents were somehow given to the iron bar, such that the bar, when the current is flowing, becomes a super strong magnet, and stops when the current stops. Faraday, in the summer of 1831, used this electromagnetic idea of coiling wires around iron, and wrapped a wire around one side of an iron ring, and another wire to the opposite side of the iron ring. One wire was connected to a battery, the other to a galvanometer. Faraday discovered that the galvanometer's arm would move briefly when the current was turned on or when the current was turned off. The current had induced a current in the second coil. To Faraday, this meant that there was some sort of tension in the state. To better understand what was happening, Faraday experimented with a permanent magnet instead of an electromagnet, and found that he could move the needle, like that of the last experiment, by moving the permanent magnet in and out of the coil of wire. The motion of the magnet past the coil caused or induced a current in the wire. Faraday knew that magnetic forces could be seen with the use of iron filings, and he used this visual of the lines of force to show the law that the magnitude of the current is dependent upon the number of lines of force that pass through the conductor in a unit of time. Faraday then quickly followed that discovery with the idea that a continuous stream of electric current can be produced by the spinning of a copper disc between the poles of a powerful magnet. This dynamo was the first design of the electric motor that we use for just about everything every day. Faraday, being of a lower class and having gained all his learning from books he binded as a bookbinder, was either unwilling or put down for his speculative ideas, and did not tend to share them with other scientists, except for his supervisor Davies and a few others. However, on April 11th, 1846, a colleague of Faraday's was to give a lecture at the Royal Institute in London. But he had terrible stage fright, and at the last moment panicked and ran out into the streets, leaving Faraday to cover him. Unprepared, Faraday briefly discussed his speculative theory of the lines of force. These speculations caused a great stir in the community, but as Faraday did not have the mathematical skills to back up his claims, most people did not follow through with his speculations. Faraday had received a request to convey his speculations by a one Richard Phillips, Esquire. The letter Faraday wrote to Mr. Phillips was titled, Thoughts on Ray Vibrations. In this endeavor to explain himself, Faraday writes, quote, The point intended to be set forth for the consideration of the hearers was, whether it was not possible that the vibrations which in a certain theory are assumed to account for the radiation and radiant phenomena may not occur in lines of force, which connect particles and, consequently, masses of matter together, a notion which, as far as it is admitted, will displace with the ether which, in another view, is supposed to be the medium in which these vibrations take place. Perhaps I am in error in thinking the idea generally formed of the ether is that its nuclei are almost infinitely small, and that such force as it has, namely its elasticity, is almost infinitely intense. But if such be the received notion, then what is left in the ether but force, or centers of forces? As gravitation and solidity do not belong to it, perhaps many may admit this conclusion. But what are gravitation and solidity? Certainly not the weight and contact of the abstract nuclei. The one is the consequence of the attractive force, which can act at distances as great as the mind of man can estimate or conceive, and the other is the consequence of the repulsive force, which forbids forever the contact or touch of any two nuclei. So that these powers or properties should not in any degree lead those persons who conceive of the ether as a thing consisting of force only, to think any otherwise of ponderable matter, except that it has more and other forces associated with it than the ether has. It may be asked, what lines of force are there in nature which are fitted to convey such an action and supply for the vibrating theory the place of the ether? I do not pretend to answer this question with any confidence. All I can say is that I do not perceive in any part of space, whether to use the common phrase, vacant or filled with matter, anything but forces and the lines in which they are exerted. The lines of weight or gravitating force are, certainly extensive enough to answer in this respect any demand made upon them by radiant phenomena. And so probably are lines of magnetic forces. And then who can forget that Monsanti has shown that gravitation, agration, electric force, and electrochemical action may all have one common connection or origin, and so, in their actions at a distance, may have in common that infinite scope which some of these actions are known to possess. The ether is assumed as pervading all bodies as well as space. In this view now set forth, it is the forces of the atomic centers which pervade and make all bodies, and also penetrate all space. As regards space, the difference is that the ether presents successful parts of centers of action, and the present supposition only lines of action. As regards matter, the difference is that the ether lies between the particles, and so carries on the vibrations, whilst as respects the supposition, it is by the lines of force between the centers of the particles that the vibration is continued. As to the difference in intensity of action within matter under the two views, I suppose it will be very difficult to draw any conclusion. For when we take the simplest state of common matter, and that which most nearly causes it to approximate to the conditions of the ether, namely the state of the rare gas, how soon do we find in its elasticity and the mutual repulsions of its particles a departure from the law that the action is inversely as the square of the distance. In 1849, William Thomas, commonly known as Lord Kelvin, in a letter to Faraday, explained mathematically how Faraday's predicted magnetic fields should affect the plane of polarized light. This led Faraday to reattempt his old experiments, and was able to prove that magnetism and light are related, in what has come to be known as the Faraday effect, which in simple terms demonstrates that a magnetic field can be used to rotate a polarized light, or, even more simply put, a magnetic field can control light. In 1852, Faraday wrote a paper entitled On the Physical Characteristic of the Lines of Magnetic Force, in which he cautiously shares his speculative philosophy on what he called force lines, and their role in the process of action at a distance. The scientists and philosophers of the last 2,000 years were attempting to get rid of this action at a distance, using the ether as some sort of mechanism, which was getting more and more complex. By this time, Faraday had held an entirely different view of that ether, no longer believing, like the others, that it was composed of particulate matter, but rather that the ether was the field which was capable of supporting the tension of electricity and magnetism's lines of force. The work of Faraday led to the work of James Clerk Maxwell. 14 years before the famous Michelson-Morley experiment conclusion, in 1873, James Clerk Maxwell had just completed his treatise on electricity and magnetism. Maxwell's treatise refrained from making claims about the ether, stating within, quote, "These and many other phenomena of electrical discharge are exceedingly important, and when they are better understood, they will probably throw great light on the nature of electricity as well as the nature of gases and of the medium pervading space. At present, however, they must be considered outside the domain of the mathematical theory of electricity." Maxwell, like Faraday and Newton before him, did not want to lose the facts of reality to speculations on the ether, and therefore none of them came to anything but physical truths to construct their mathematical formulations. All of Maxwell's equations are derived from physical observations, and the equations explain how the fields of force are constructed as demonstrated by the physical experiments that defined them. The addition of the Lorentz force law completed the understanding, as the force law explains how these fields will affect the things within them. Maxwell therefore showed how objects in the field create forces, and how those forces would in turn affect the objects in the field. Let us get a better idea of what a field is. A field is an abstract idea that says there can be assigned a value for each point in space and time. This value represents some physical quantity. For example, we can take a room and divide it up into imaginary boxes of equal volume. Say each box is 1 cubic foot, meaning extends 1 foot east to west, extends 1 foot north to west, and extends 1 foot ground to ceiling. If the room is 1,000 cubic feet, 10 feet in each direction, then there are 1,000 imaginary boxes stacked 10 by 10 by 10. This room can be said to become a field when we put a thermometer inside every box. The field in this case would be a scalar temperature field. The values at each point in the space of the room would be the temperature at that specific location, and those temperature readings would change over time. We can also stick other measuring devices in each box, like a gravity detector, an electromagnetic detector, a photon detector, a wind speed detector, and so on. Each of these detectors would register some physical quantity, which is the result of having received energy from the environment. The field of forces of gravity would have vectors which point in the direction of the Earth. The electromagnetic detector would register some electric and magnetic fields of force, etc. The fields then are just our way of dividing up space and time so that we can understand what each point in space and time is experiencing at any given moment. Faraday's lines of force require time to propagate, and Maxwell helps explain this with a real example. An electric current can cause a magnetic field to appear, but it doesn't have to be an electric current. A time-varying electric field, a short vibration in the electric field, can also cause a time-varying magnetic field, a short vibration in the magnetic field. And a time-varying magnetic field can cause a time-varying electric field. And this self-propagating electromagnetic field can be written as a wave equation, and the speed of this wave happens to be the same as the speed of light. Leading to the conclusion, quote, "The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws." Conclusion: that which exists where nothing isn't. The little stuff is that which is where nothing isn't. It fills the universe and can be otherwise called the ether. The ether, if it had the ability to do so, might wish to quote Mark Twain to say, "The reports of my death have been greatly exaggerated. The ether is alive and well despite the claims to the contrary." Today, that ether has taken on the name fields or even space-time. The little stuff is not particulate, but that was never a requirement for Ayn Rand or Leonard Peikoff. All that was philosophically necessary was that something exists where nothing isn't. Today, we know that light is a packet of energy, an electromagnetic disturbance in an electromagnetic field, and that its speed is a result of its nature as a massless energy chain reaction of time-varying oscillations in the ether. We have walked through the history of the ether and have come out on the other side having learned that the ether didn't die. The bad ideas about it died, and what was left standing has led to the marvels of the world around us today. The physics of field theory, which has grown from this discovery of this new ether, has advanced science and technology tenfold, if not more, much, much more. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.